Hello all and welcome again. So in this video, we are going to write the unit test cases for the EIP-712 verified smart contract, which we have completed in the previous video. So let us get started with it. The first question which is asked by AI is, in a Foundry test, to produce a valid EIP-712 signature, you need a private key to sign with. Foundry gives you a cheat code for this. Do you know which cheat code produces a signature VRS from a private key and a hash? Hint, it lives in the VM object. When it says it lives in the VM object, here we already have a counter.t.sol file, which is counter test file. So from here, let us click on test. And since we want to deal with standard sheets, so here we have standard sheets. And inside this, we will try to look at signature to get an idea about VRS. I don't think we have a valid signature code over here. So let us go back to test.sol. Here we have vm.sol. Click on this. Here do we have signature? Yes. Okay. Sign compact. Signs data with a wallet. Returns a compact R, BS as per EIP 2098, where BS encodes both signature S value and the recovery ID B as single bytes 32. So there are various versions. Okay. So sign compact, signs data with a wallet. Then we have sign compact, which takes a private key and a digest and returns bytes 32R and bytes 32VS. So this signs digest with private key using the SECP 256K1 curve. What are the other options? With signer provided to the script using, okay, sign compact, signs digest with signer provided to the script. Then we have sign ed 25519, sign with nonce unsafe. Then we have only signed. Then we have only sign function. Okay. So I think this is the key. Let us go back. Yes. Inside vm.sol, we have a function. This gives us VRLS given private key and data to sign. Yes, exactly. vm.sign private key digest is a cheat code we need. Now, before writing tests in Foundry, how do you derive the address corresponding to a private key? This matters because in our execute function, we pass signer and that needs to match the address that's signed with the private key. How do you derive the address corresponding to a private key? Corresponding to a private key. So do we have a get address function? Key get block number, block timestamp, chain ID. Then 6 get record. The last is fs metadata low. From here can be standard JSON, standard math, normal utils, standard constants, not of our use, standard cheats. Instead of searching this inside, let me go to the Foundry documentation. Get started, and we have to search for how do you derive the address corresponding to a private key. Let me search for get address. Get here it is, get address from key store. So get address from private key, get address from okay test signature verification. Here we already have derive, get a private key and address from a test mnemonic. Here it is, cast wallet public key kill, but this is using cast. We want to derive it inside get public key from private key. Here we have an example test signature verification. I think this is what we are doing right now. Let me check. Here it is. It can be, the address can be fetched using the address can be fetched using vm.address and passing in the private key. So the pattern for every test will be private key, signer, build the digest. Now what is the digest you pass to vm.sign? Write it out in terms of the contract's components. The digest is our transfer struct members, that is to address doing 256, then amount uint 256 and nonce uint 256. This vm.sign needs a byte 32 hash, not the raw struct. Think about what the final hash is. That the contract computes inside verify. That's exactly what you need to pass to vm.sign, because the contract will recompute that same hash and verify it matches. Write out the full digest computation you'd need in the test. This is simple. Coming back to the EIP-712 verifier contract, the final digest. This is the domain separator. Execute, verify. Inside verify we have this final hash, right? This is the final digest. The domain separator will be fetched from the contract as it is initialized in the constructor, or since we are using solidity tests, you can also calculate the domain separator in the test menu. And since hashStruct and verify are now internal, your test can't call them directly on the deployed contract. So in your test, you have two options: replicate the hash computation in the test file manually, or expose a public wrapper in the contract for testing purposes. Which approach do you think is cleaner for production code and why? First one, replicate, is the better approach for production code, because those functions need to be internal and in the production environment they are going to be referred by the calling function. Here we are ensuring that it works as expected. Hence, replicate is the best option. Okay, now write the Foundry test file. Start with just the happy path test. Valid signature returns true. I execute. Succeeding. Structure to follow. Deploy the contract. Set up signer using vm.addr address. Build the transfer struct. Compute the digest manually in the test. Sign with vm.sign. Call execute and assert it succeeds. But prior to that, let us have a look at the counter.p.sol file, which is the counter test file for the counter smart contract. We will create our EIP-712 verify.p.sol file on the same lines. Let me copy this. Create a new file .p.sol. Let us open this file on the right side. So first thing is, let us copy this as it is. Here we will use the pragma version to be 0.8.06 to be in line with the EIP-712 verify contract itself. Then we will import the test contract, since our test contract will be inherited from this contract, and we will also import our EIP-712 verifier contract from /src/EIP-712 verifier.sol. Then after that, our contract EIP-712 verified test is test. First thing is, we create our main contracts object. So EIP-712 verifier public EIP-712 verifier. Then this setup function is responsible for creating our contract instances. This will be a public function, and from here we will call our 712 verifier. Will set its value to view EIP-712 verifier. Now our contract accepts, the constructor accepts, and it is name and version. So we will pass on the name and version. Let us call the name to be name. Let us call the name to be Zignaly, and we will set the version to be 1.0. Once for this will give us our EIP-712 verifier contract instance. After that, what is the next instruction? First one, deploying the contract is done. So we have deployed the contract from within the setup function. EIP-712 verifier is equal to new EIP-712 verifier, passing in the name and the version. After that, the second step is set up signer using vm.addr. So we will declare one more state variable, address public signer, and that signer will be set to signer equal to vm.addr, that it accepts a private key, right? So what we will do, would create bytes 32 private key is equal to 256 private key is equal to show into 2561. Okay, then we will get the address from the above dummy private key. So in the setup, we have deployed the contract, we have set the signer address. Next is we have to build the transfer struct. Now the transfer struct inside our smart contract. Okay, so we just copy paste it. Efficient for testing purposes. Build the transfer struct, compute the digest manually in the test. Okay, so struct, this is transfer. Also bytes 32 constant EIP-712 domain hash. We'll also copy this. We will copy the domain separator logic. Okay, so let me define. I think we can get domain separator by calling this EIP-712 verify dot domain separator. So next step is we have the transfer structure, then build the transfer struct. This simple, we will set the to address to be, let me use address receiver equal to address of 2. So receiver is set and event 256 amount equal to 1 ether. 1 ether. So this will be 1 followed by 18 zeros. 3, 6, 6 into 1 ET. So amount is 1 ether. And we will also use a variable event 256 currentNonce. You would set this to 0. So in the setup function, we have created the contract. We have set the signer address. You will also get the nonce for this correct signer or currentNonce equal to EIP-712 verify dot derives, and we will pass in the signer address. So we have got the currentNonce as well. After this, what else is remaining? Build the transfer struct, compute the digest manually in the test, sign with vm.sign, call execute and assert it succeeds. Give it a go. So transfer setup, in setup, contract is deployed, signer is done, currentNonce is done. What else do we need? To an amount are already defined. Let me call this instead of receiver, name this as to avoid confusion. So setup part is done. Function, let us verify counter test implements. So we'll say function test execute. Thing is visibility will be public. Yes. Test execute public. So this execute function expects signer. You already have signer. Then transfer call data transfer. Okay, so here we have our structure. We'll initialize this. So transfer memory transfer equals our transfer structure, wherein 2 is 2, amount is amount set, and nonce is nothing but a currentNonce. So we have built the transfer struct. It's built as follows. Then after that, so transfer struct is built. Now we need the signature component VRS. So for that, we are going to use vm.sign privateKey. But prior to that, we need the digest. And the digest is nothing but our final hash. So this is our digest. Now to get this, let us do pipes 32 digest is equal to kitchak256 hash kitchak256 of kvi dot encode packed. Here first we pass in the prefix string, then after that domain separator will be called from our EIP-712 verifier contract, because domain separator is a variable state variable of type public. So by default, Solidity defines a getter function for it. Hence, we are making use of that. So for the digest part, we have prefix string domain separator, then hashStruct of transfer. Now, when we say hashStruct of transfer, so what exactly it is doing? It is calculating this part. So in order to do that, what we will do is we will copy this entire code over here. That is, let me copy this and paste it over here. We haven't defined the transfer type hash in this test contract. We'll do that as well after this. Done. API.encode, let me take this menu line. Then we have API.encode path. So transfer type hash, let me copy that. Bytes 32 constant transfer type hash. Where can we see? Here we have transfer type hash also, and this is key feed, one more parenthesis. Yes, now it is complete. Everything moves to more one tab inside. So just group. Yes, so this is how we construct the final digest. Constructing the final digest as it is done inside the main contract. Constructing the final digest as it is done inside the main contract. Once we have the digest, then we are going to call vm.sign on that digest. vm.sign privateKey and the digest. So get hold of the signature components v, r, and s. Since it is a tuple, hence it will be written inside parenthesis uint 8v bytes 32 r and at last bytes 32 s. This will be returned by vm.sign, which accepts the digest, the private key. So we have already defined up private key and the digest. Now we have the signature component, the digest, and the signer. So what we will do is we are done with vm.sign. Now we will call execute and assert it succeeds. We are going to call execute and assert it succeeds. Call execute and assert it succeeds. So for that, execute for EIP-712 verifier.execute. What different parameters does execute take into consideration? Execute takes in signer. Yes. Then our transfer struct. Then after that, v, r, and s. How do we assert? Okay, let us go to sign. assert equal function assert equal boolean left boolean right internal. Okay, got it. So what we will do, bool result equals, since our execute function, it's an external function, it calls verify. It calls verify, internal view returns bool, which we are checking over here. Then we update, we check the nonce as well. After that, temp nonce we emit. So what we can do is, after calling this, prior to calling execute, nonces of signer is equal to 0. So assert equal EIP-712 verifier dot nonces of signer is 0. Assert that left is equal to right. Okay. And then after calling execute, nonces of sign up equals 1. So what we will do, so if this works, everything is good, and we have successfully written our first test, which is test execute. Let us compile this. So where forge combine. So it says index expression has to be a type, mapping, or array. Got it. So it should be parenthesis and not square bracket. Forge compile invalid implicit conversion from struct transfer memory to invalid type for argument in function called transfer. Invalid implicit conversion from struct EIP-712 verified test dot transfer memory to struct EIP-712 verified dot transfer memory requested. But don't you think both are one and the same? So here we have struct transfer. Struct transfer, how to fix these? You can try to that. Here is the test file. Excellent test structure, clean, right? Commented and the digest computation is correct. One bug, look at your final assertion. The comments is 1. Okay. Be warrant done. After that, compilation is giving error. I understand the error. Since we have defined transfer struct in the unit test file as well. Somehow it is contradicting with the transfer struct of our make content. You have two transfer structs, one in the test, one in the contract, and Solidity sees them as different types even though they have identical fields. The fix is simple. Remove the transfer struct definition from the test file and import it directly from the contract. How about you reference the contracts transfer struct type in the test file? How about you reference that? Okay, got it. So what I will do is transfer to know this. Here we use EIP-712 dot transfer. Instance, not a type. You reference type from a contract using the contract name, not the instance name. How would you fix that? Close button. You're getting it wrong. Who are getting it wrong? On add set EIP-712 verifier equal to vm system in the setup function. To reference a type defined, okay, we use the contract name, not the instance variable. Oh, got it. So it should be EIP-712 verifier. It's the contract time. That sounds already knows where to find the transfer struct definition. Also remove the local struct transfer definition. Let me try it compiling now. Force compile. Okay. Got it. It should be EIP-712 transfer. Yes, so compilation is successful. It says use of inefficient hashing mechanism, consider using inline assembly. This is very good, pointed out by, you could say, Foundry. We are going to address this, but not right now. But we will address this at the end of the session or in the next video. So now let me go on forge test. Forge test. Yes, so it says it has called test execute. Suit result is okay and the test has passed. The compilation was successful and also the test got executed successfully. Forge test. Now write the remaining tests from your list. Invalid signature returns false. Tamper with the signature or the struct data after signing. Address 0, signer reverts. Pass address 0 as signer. Replay attack. Submit the same signature twice. Second should fade. Write all 4, take them one at a time and show me each as it passes. So the next test case is that of invalid signature returns false. But in order for invalid signature to return false, what we are doing is, okay, so invalid signature return false will basically hit this require statement. That is simple. First, now the second test is function test rewards when signature is invalid. When signature is invalid. For that also, most of this thing will be seen. That is transfer construction, transfer struct construction, then the digest calculation part, then the private key part. Okay, so what I'll do, I'll create a function and we'll name the function as test setup. This function as test setup, and inside this test setup we'll move these redundant stuffs. That is, here we have, okay, now this test setup, it must return public returns bytes 32. Should it be public? It should be public pure, because it's not reading it. Yes, it is reading from the state, so it must be set to public view, and then shell will call bytes 32 digest equal to, instead of test setup, we'll call this function as getDigest. Okay, digest. So this will give us our bytes 32 digest, and then all that will change is the assertion part. That's it. So let me comment the below function, and after refactoring, let me call or run the test cases to ensure that everything is working as expected. Forge test function variable struct or modified declaration expected. Where I think I have left out something. Okay. Compiling one file, compiler run undeclared identifier transfer at line number 63. Line number 63. Okay, here it is, 63. So this must return public, and in solidity you cannot return struct. So is there a point of, can we return a struct in solidity? I don't think so. Let us try it out. Returns either it will compile or it will not compile. We'll try that out. So return digest cover transfer. Let us try compiling this. Okay, undeclared identifier transfer. Okay, so here we have our digest part. Then our transfer struct. Compiling data location must be memory or call data or return parameter. Okay. See here, getDigest. So memory. So what I'll do, we'll have a named return. This will be digest, and second return type will be transfer. So here would directly assign the value to those variables. In case of named return, there is no need to write an explicit return statement. Now let us try compiling this. So it says bytes 32. Okay, my bad. Here also should be memory transfer. Compiling, yes. So even after refactoring our contract, we are able to test execute the function successfully. After that we have we are going to test reverts when signature is invalid. Again, let me copy this two part. This is going to be constant across our tests. So we have getDigest and transfer struct. So that vm.sign, then we will call execute and assert it reverts. But prior to that, let us check the documentation for assert revert. I think we have assert foundry solidity assert revert unit test example. To write unit tests, okay, testing foundry. Let me go to the documentation. So testing, writing tests, test increment, test set number. This is easy. Then what we have, okay, so here we have fail unauthorized, stack places, full traces, then match test, match contract. So the next time we will run match contract and pass in our contract name such that only the test cases for our contracts are run. Let us do that. Let's go to it. Okay, match contract, EIP-712 verified test, no visibility specified. Did you intend to add public? Okay, my bad. QP public clear. Yes, so it has run both these test cases, but in a second test case, we haven't asserted anything yet. So let us do that. What I'm trying to figure out is there's a nice way to catch revert statements or revert tests in Foundry. First testing, load, table testing, which enables the definition of a no, not needed. Mutation testing. This also symbolic more testing. Yes, here we have testing reverts. So vm.expectRevert, what we will do prior to calling this, we'll say vm.expectRevert. Let me copy this. vm.expectRevert, and the expected revert statement is since verify will return false, so we must get verification field. So what I'll do in order to make this signature invalid, I'll pass in the value of v as 108. Now let us try running this. Yes. So indeed, our expect reward is working as expected. It says okay, 2 passed, 0 failed. So this has executed successfully. Now, if I remove this and pass in B, then this test should fail, which would ensure that this line was indeed getting executed. Here it is. It says fail next call did not revert as expected. Now, in order to make it revert, again we are changing the value of V to 108. Again, let me rerun this test. So now both the test cases have passed successfully. After that, let me go to Claude. It says address 0 signer reverts, pass address 0 as a signer. This one is also simple. function test rewards when signer is address 0. Again, the visibility is public. These two lines will remain the same. Let me copy this entire thing. Paste. So here we want to pass the signer to be a 0 address. In that case, I must get the revert to be invalid signer. So here we'll pass in B, passing signer as the 0 address. Show signer address of 0. So this should revert with invalid signer. Let us run this. Clear the terminal. Exactly, it is working as expected. Now the next test case is replay attack submit the same signature twice, second should fail. So function test rewards when replay attack. So again copy the I would say copy the entire part. Here since this should succeed, so remove this vm.expectRevert and change address 0 to that of the signers. When we say dot execute, so dot execute emits an event executed. Let us capture this event in our test case. So this is given in the documentation. Here we have testing events. Click on testing events. And here it says vm.expectEmit the parameters, then emit. To verify events are emitted. Then we call token.transfer vm.expectEmit. What is this true, false, true? Say cheatcodes, warp rule. Oh, what is this? Testing events. We mean dot expect event. Let us do that. So here you will add vm dot expect and mock no expect emit. So what does true, false, true? Alice go 100. What is this true, false, true? In our case, since our event emits two parameters, which is signer and tempance. So let us use that, and hence I have used two true values. I'm not. Let us see if this works. If not, then we'll dig through the documentation to understand which all things needs to be passed as true. Then this should emit executed event. Now this executed is defined inside the EIP-712 verifier dot executed, and it should take in the address of signer. And also when we talk about nonce, what is the nonce value? I think the nonce is currentNonce. No, but after, yes, currentNonce. How can we get that? So we will have to store the currentNonce. EIP-712 verifier dot executed signer. Take currentNonce yield 256 currentNonce equal to EIP the contract instance dot nonces of signer. So this will be emitted and guidance. Using this, we will know that the first call has executed successfully. Then after that, we will try replaying the same signature In that case, it should fail with invalid nonces. So let us do that. Here we will do vm.expectRevert invalid nonces, and again we will call execute. So first way it will be executed successfully, and second time it will revert. So let us try run this. So it says currentNonce. This declaration shadows an existing declaration. So how are we using? Okay, let me use this as pivot constant. Is variable shadow is addressed. Member expectEmit not found or not visible after argument decay dependent lookup in contract vm. vm.expectEmit. But why it is let's go to Google AI. Foundry vm.expectEmit. Has it been reviewed? If yes, what is its decreasement? Okay. All requirements still supported but no longer strictly required. Okay, will to see it. Got it. Dot expect you bit. Okay, done. So we have also tested out reverts when replay attack happens. That is, first it got executed successfully and emitted the event executed with signer and temporary nonce, which was a current nonce. So here we can also do this check apart from this, that yes, prior to call in, this was the signer's nonce. I think that would be redundant. This is enough. Now we have tested rewards when replay attack happens. That is, the same signature when used for the first time it got executed successfully. When it was used for the second time, so it showed invalid nonces. After that, we have our last test case, which is cross contract replay. Deploy a second 712 verifier. Try to use a signature from the first on it. Okay. Test function best cross compact replay. So in this case, what we will do is we will deploy another contract EIP, another EIP-712 verifier, another EIP-712 verifier. This will be new EIP-712 verifier. We will pass in the name to be Paradex and the version to be 1.0. What we will do, we will create signature for the first EIP-712 verifier and then use that on this contract. Let us try doing that. So first we will call getDigest. We will get the digest as well as the signature components. This is done. Then we are going to call our execute function, but notice here this is our first EIP-712 verifier, and now we have deployed another EIP-712 verifier. So we are going to use this contract. So this should prevent cross-contract replay. And where would this fail is for another EIP-712 verifier, the final hash, it will be, in our case, the final hash is computed using the domain separator of our first domain separator of EIP-712 verifier contract. And for that contract, the name and version is Zignaly and version is 1.0. For another EIP-712 verifier, the name is Paradex and version is 1.0. So when this final hash will be computed inside the verify function, right? For this another EIP-712 verifier contract, in that case, this domain separator will be different. And when we call this original sender, when we call ecrecover on this final hash, given the valid VRS, so this will return address 0. So what this verify function will return? This verify function will return false. When this verify function returns false, so it will show or it will revert with verification failed. First, prior to adding expect revert, let us call this as it is. It should revert. The transaction should not succeed. Clear? So here it shows failed. That is 4 passed and 1 failed. And the reason is verification failed. Test contract replay, which is as expected. This is failing at this point, which is the correct working. So let me add vm.expectRevert verification failed. Now let us try rerunning the test cases. Here it is. All 5 test cases passed. Since we have completed this, write all 4, take them one at a time and show me each as it passes. So here it is. The entire test cases. And the terminal showing the tests pass. So B is unused. How? Because you're hard-coded. How do you silence this warning in Solidity? I can silence this warning in Solidity, where is 108. Here it is. Not take into consideration the v variable. And then we click on forms from pile. There should not be any warning. Okay, expected, comma, but got identifier. Or completely skip this. Now we should compile it. Done. So what we have, thus mutable variables should use mixed case. Consider using another EIP-712 verifier. That's okay, okay, got it. So let me take into consideration this warning as well and rename this to a mixed case. Done. This is fixed. Now let me run through this compile. Done. So where is 808, 108, 108? Create deployed. How do you sites? We can silence this warning by ignoring the returned variable as should be. Wait. There are some more warnings which should be addressed. Then give the final note. So as I told you earlier, right now, Foundry has reported that use of inefficient hashing mechanism, consider using inline assembly. Use of inefficient hashing mechanism, consider using inline assembly. For calculating final hash, we are using ketchat256 and then as we discussed ABI.encode packed, the prefix string and domain separator. And also in the other function also we are using ketchat256 hash. But these are inefficient hashing mechanism. And what Foundry is suggesting? Foundry is suggesting to use inline assembly. How can we make use of inline assembly? Now let us take this to Claude and look what instructions does it give. Okay, let me ask you a question. The warning says use of inefficient hashing mechanism, consider using inline assembly. Why would inline assembly be more efficient than encode? Or think about what ABI.encode and ABI.encode pack do under the hood before the hash is computed. They pad the data to 32 bytes when needed, which results in gas consumption and thus making them inefficient. Allocate memory, copy data into it, then pass the memory pointer to ketchat256. That memory location and copy costs gas. Inline assembly with ketchat256 can hash data directly from its memory location without an intermediate copy, saving both memory allocation and copying costs. Before we fix this, an important question. This is a forge-lint note, not a compiler error or even a warning. Do you think you should always follow this suggestion? What trade-off are you making if you rewrite this with inline assembly? Think about readability, auditability and maintainability. Readability will be affected. Readability will be for sure affected. Auditability will also be affected as inline assembly codes may be missed or the chances of catching bugs for inline assembly is low. Maintainability, the next developer must know inline assembly code. Inline assembly is more gas efficient, harder to read, harder to audit, bugs are easier to miss. Requires the next developer to know UL or assembly. High level solidity. This is a learning project and a verifier contract correctness and auditability matter more than squeezing gas here. Opens up its own implementation uses high level solidity for exactly this reason. You have 2 points. Suppress the linked note with a forge format, disable next line. Okay, let me do that. I think I should fix it with inline assembly as a learning exercise. I would want to do 2, but in the next video. So the session is completed. So what I have built today from first principles. First is EIP-712 verify fully functional, all 5 Foundry tests passing, valid signature, invalid signature, zero address guard, replay attack prevention, cross contract replay prevention. Next session, we will use inline assembly optimization for KCHAC 256 calls, understanding Joule and why it's more gas efficient, benchmarking gas before and after. So thank you all for joining. I hope you would have learned something valuable. If yes, please do like, share and subscribe. Thank you.